Okay, so you sent over some research about web agents, specifically the BrowserGym ecosystem. This paper, the BrowserGym ecosystem for web agent research, really dives deep. We're talking about AI systems that can interact with websites just like humans. It's pretty mind-blowing.
Yeah, it's really cutting edge stuff. What's fascinating about BrowserGym, like it says in Section 1, is how it's trying to standardize how we evaluate these web agents. See, before, the research was all over the place. Section 2 talks about this. Different benchmarks use different methods. It was a mess. Early ones, like MiniWo from 2017, focused on pretty simple tasks. In fact, even its 2018 extension, MiniWo B++I, still kept things simple and in these synthetic environments. It's all explained in Section 2.
So kind of like testing them in a simplified version of the internet, a very controlled environment.
Exactly. But AI's come a long way since then. Newer benchmarks, take Web Arena for instance, use these replicas of actual websites. Section 2 talks about that. Way more complex. But that made it really hard to compare progress across research efforts.
Right. It's like trying to compare athletes from different sports. Totally different scoring systems. Who's really the best?
That's the problem BrowserGym tackles head on. Section 3 really outlines this. Unified environment, clear rules like a level playing field.
Makes a lot of sense. The paper also mentions AgentLab, this toolbox for building, testing, analyzing the agents. That's where things get really interesting.
Oh,
Yeah.
absolutely. AgentLab, as you see in Figure 1, provides a whole set of tools, makes research so much smoother, all explained in Section 5. Plug in different AI models, test them across those BrowserGym benchmarks. There's even a tool to visualize how the agent's making decisions. It's called Agent X-ray.
So researchers can literally see how the agent thinks.
Exactly, and that focus on reproducibility, crucial. As they highlight in Section 5.4, web environments are always changing.
I can imagine. Even a small website redesign would mess things up.
You get it.
Oh.
Section 5.4.1 goes into this. Even minor changes can throw things off. You might think an agent got smarter, but it's just the website that changed.
Yeah, you wouldn't want to draw the wrong conclusions.
Right, so BrowserGym and AgentLab are packed with features to ensure reproducibility. Tracking software versions, standardized actions, all the details are there in Section 5.4.2.
So others can precisely replicate experiments and verify the findings?
Exactly. And there's this really cool thing called the reproducibility agent. Section 5.4.2 describes it. It reruns actions, compares outcomes. It can even show you visually, like changes in website HTML, if something's different from the original test.
That's awesome. Make sure we're comparing apples to apples when we're evaluating agents. Now let's talk about those benchmarks. The paper, Table 1 to be exact, lists 6, MiniWo P+, Plusco Web Arena, Visual Web Arena, Work Arena, 3 levels there, WebLine X, and finally Assistant Bench. Give us a tour of these playing fields.
All right, well, MiniWobi plus Oscilla, we touched on that earlier. It's like the synthetic UI tasks. Simple, controlled, like we talked about. Section 2 covers it.
And Web Arena, that's where you get those replicas of real websites, right?
Exactly. Web Arena, detailed in Section 4, recreates sites within a controlled environment. Agents book flights, order food, even play games. Much more realistic than MiniWabi plus pluses.
So the stakes are higher.
You got it. And then there's Visual Web Arena. Things get even more complex there. Images are part of the tasks now.
Ah, so the agent has to understand the visuals, not just the text on the page.
Right. Visual Web Arena, Section 4 explains it, really tests if the agent gets the connection between visuals and text. Think of finding a product based on an image or matching a description to a picture.
That's next level stuff.
It is. Then we move on to Work Arena, described in Section 4, focused on tasks you'd see in a company. They use a platform called ServiceNow.
ServiceNow, what's that?
It's software companies use to manage internal stuff, expenses, service tickets, approvals, the whole works. Work Arena simulates this environment. It tests how well an agent could function as a digital employee. And they have levels of difficulty. L1, L2, L3. Section 4 mentions them. Understanding instructions, following procedures, dealing with unexpected stuff, the whole 9 yards.
So it's like a corporate ladder for AI.
You could say that. Next up is Webla X. Section 4 has the details. It uses data from real human interactions. So the agent is trained to mimic what real people do on websites.
Learning from the best, huh?
Exactly. And finally, we have Assistant Bench, which they describe in Section 4. This one gives the agent tasks that involve going to multiple websites, gathering information. Like you give it a mission, find the best travel deals based on these criteria.
So it has to act like a real intelligent assistant.
Precisely. An Assistant Bench, unlike some others, actually uses live websites, the wild west of the internet.
The ultimate test.
You got it. So the researchers, as they explain in Section 6, ran these experiments. They took a generic agent, powered it with different AI models, the best ones out there, and ran them through all these benchmarks.
Okay, so we have the playing fields, the athletes, and the judges. Time to see how they scored.
Absolutely. The results are in Table 2. They focused on task success rate. How often did the agent actually complete the task? And right away, one thing popped out: the performance of Claude 3.5 Sonnet, a model from Anthropic.
Sounds like this Claude was the star athlete.
You could say that top scores on almost all the benchmarks: Web Arena, Work Arena, even WebLine X. Really good at understanding instructions, navigating those interfaces, and completing those multi-step tasks.
Impressive. How did the other AI models stack up against Claude? What about those GPT models everyone's talking about?
Well, GPT-4o did pretty well, but consistently behind Claude. But here's the thing. They saw a big improvement in GPT-4o's performance compared to earlier tests on Web Arena and Work Arena L2.
So it's getting better, even if it's not the top dog yet.
Exactly. Shows that OpenAI is working on those web reasoning skills.
Makes sense. What about the open source models, like Llama? Those probably fewer resources behind them, right?
You'd think so, but they actually did surprisingly well. Llama, particularly the 405B version, even beat GPT-4 Mini on some benchmarks.
So you don't need to be a giant corporation to make a dent in the AI world.
That's the exciting part. Shows what the open source community can do. Now, any surprises? Were there any benchmarks where the agents really struggled or did better than expected? One thing that stood out was Assistant Bench. All the models, even Claude, had pretty low scores there.
Really? Assistant Bench is all about gathering information, right? That's like a core web agent skill.
It is, and that's what makes this finding so interesting. Section 6.2 delves into it. They think the BrowserGym API, which is mainly about direct actions on a page, clicking, filling forms, etc., it might not be the best fit for tasks that are all about information.
So it's like giving the agents the tools to interact, but not necessarily the skills to deeply understand the information on the page.
Exactly. Something to think about for the future. Maybe the API needs some tweaks to handle those more complex information tasks.
It seems we've come a long way, but there's still a lot to explore in the world of web agents, especially when it comes to those information-heavy tasks that are becoming more and more common online.
Couldn't agree more. It's a constantly evolving field. These findings show us what we're doing well and where we need to focus our efforts. So we've touched on how BrowserGym creates this level playing field, this unified environment for web agent research. But how does it actually achieve that?
I was wondering that too. Section 3 mentions something called the OpenAI Gym API. Is that part of the solution?
It is a big part. Section 3 explains it really well. OpenAI Gym API is like this gold standard in reinforcement learning. Everyone uses it. So BrowserGym, by using that framework, Figure 3 shows it visually. It lets researchers integrate different benchmarks and agents really easily. No need to start from scratch every time.
So a common language that everyone in the field can understand and use, that fosters collaboration and keeps things consistent.
You got it.
Yeah.
And BrowserGym does more than just provide a common interface. It also gives these web agents a rich and comprehensive observation space. Section 3.1 goes into detail, and Figure 2 illustrates it.
By observation space, you mean the information the agent gets about the web page it's interacting with, right?
That's right. And BrowserGym provides this information in several formats, starting with the raw HTML of the page.
So the agent sees the underlying code of the web page, like a web developer would.
Exactly. But it doesn't stop there. BrowserGym also provides the DOM document object model. It represents the web page as a structured tree of elements. This hierarchy helps the agent understand the relationships between different parts of the page.
So instead of just seeing a jumble of code, the agent gets a more organized view of the web page, similar to how a human might visually perceive it.
Precisely. Then there's the AX tree, the accessibility tree. This one focuses on how elements are presented to users, especially those using assistive technologies like screen readers.
That makes sense. This ensures that the agent understands the web page in a way that's aligned with accessibility standards, considering how users with disabilities might experience it.
You got it. Section 3.1 explains how the AX tree highlights interactive elements and those conveying important information. It helps the agent prioritize its actions and interactions.
That's a crucial aspect, ensuring that web agents are developed with accessibility in mind from the get-go.
Indeed. And BrowserGym enriches these HTML elements with additional properties, things like bounding box coordinates and visibility ratio.
I'm not sure I follow. Why are those important? What do they tell the agent?
It's about visual context, which Section 3.1 describes. The bounding box coordinates tell the agent where each element is located on the screen. And the visibility ratio indicates how much the element is actually visible to the user.
Ah, so it's like giving the agent a sense of spatial awareness, allowing it to understand not just what's on the page, but also where it is and how it's presented visually.
Exactly. And this visual information is particularly useful for agents that rely on computer vision. It helps them interact with web pages in a more human-like way.
So we've got the HTML, the DOM, the AX tree, these visual properties. It seems like a lot to process. Does the agent also get to see a visual representation of the web page, like an actual image?
You're right, that is a lot of data. And yes, BrowserGym does provide the agent with a screenshot of the web page. Section 3.1 mentions that. The other representations give structural and semantic information, but the screenshot provides the complete visual context, including things like images, fonts, and the overall layout.
So the agent can see everything, the big picture of the web page, just like a human user would.
Precisely. This visual information is especially important for tasks that require understanding spatial relationships between elements, recognizing images, or interpreting the overall aesthetic of the page.
It's like giving the agent eyes to see the web, in addition to a brain to understand it.
Great analogy. And to make it easier for the agent to work with all this information, BrowserGym uses a system of unique IDs. Section 3.1 explains this. It's called BrowserGym IDs, or BIDs. Each element on the page gets a bid.
So instead of having to refer to elements by their complex HTML tags or descriptions, the agent can simply use these shorter, unique IDs.
That's right. It makes it much simpler for the agent to reference specific elements, even if the underlying HTML is changing dynamically.
Like giving every object on the web page a unique barcode, allowing the agent to quickly and accurately identify and interact with it.
Exactly. So far, we've talked about how BrowserGym provides a rich observation space for these web agents. But what about the actions they can take?
Right, the actions are crucial. It's not just about seeing the web page, it's about interacting with it. Clicking buttons, filling forms, navigating to different pages. How does BrowserGym handle that?
BrowserGym offers a flexible action space as well. Section 3.2 goes into detail on this. This action space defines all the possible actions an agent can perform within the browser environment.
So it's like defining the agent's toolkit, the set of commands it can use to interact with the website.
Precisely. And BrowserGym provides various levels of control. The most basic action space is raw Python code, which Section 3.2 mentions. This gives researchers a lot of flexibility. The agent can essentially execute any Python code within the browser context.
Sounds powerful, but also potentially dangerous. What if the agent executes some malicious code?
That's a valid concern. And that's why BrowserGym has mechanisms to restrict the action space for safety. Section 3.2 explains that. One approach is to provide a predefined set of high-level actions, as detailed in Appendix A, Table 3.
So instead of giving the agent free rein with raw Python code, we can provide it with a set of pre-approved actions that are considered safe and relevant to web interactions.
Exactly. These high-level actions, exemplified in Figure 6, are like functions that encapsulate common browser interactions. Things like click, fill, or scroll. A more controlled and secure way for the agent to interact with the web page.
It's like giving the agent a set of specialized tools designed specifically for web tasks, ensuring that it doesn't accidentally or intentionally use the wrong tool for the job.
Precisely. And researchers can even define their own custom action sets, as explained in Section 3.2, tailoring them to the specific needs of their benchmarks or research goals. This allows for flexibility while still maintaining a certain level of safety and control.
So a modular toolkit where researchers can add or remove tools based on specific tasks they want the agent to perform. Okay, we've got the plain chill BrowserGym with its standardized observations and actions. But how do you create a new game? Or in this case, a new benchmark within this ecosystem?
That's where the extensibility of BrowserGym shines. It's described in Section 3.3. Researchers can create new tasks and benchmarks by defining two key methods: setup and validate.
Okay, break those down for me. What does the setup method do?
Setup is responsible for getting the browser to the starting point of the task. Imagine you're creating a benchmark to test an agent's ability to book a flight online. The setup method would navigate to the airline's website, maybe even pre-fill some details like the departure and arrival cities.
So it's essentially setting the stage for the agent, placing it at the starting line of the race.
Exactly. Once the setup is done, the agent starts taking actions based on its observations, and that's where validate comes in.
Yeah, so validate is like the referee, checking if the agent has successfully completed the task.
You got it. It's called after each action the agent takes. Checks if the goal of the task has been achieved. In our flight booking example, it would verify if the agent has successfully booked the flight with the correct details.
And does it provide feedback to the agent like a score or a reward based on its performance?
It does in the form of a reward. Section 3.3 explains this. A positive reward for good actions, maybe a negative reward for failures or inefficient actions.
So it's like a training system, helping the agent learn from its mistakes and improve its performance over time.
Precisely. The reward system is a key part of reinforcement learning. It guides the agent towards the best strategies for completing the tasks.
Now, the paper mentions that each benchmark comes with its own metadata and suggested parameters for evaluation. Why are those important?
The metadata, as described in Section 4, tells you about the tasks within the benchmark. Things like category, difficulty, dependencies between tasks. For example, in Web Arena, some tasks might need you to complete previous tasks, and the metadata would have that information.
So it's like providing context and instructions so you know how to use and evaluate the benchmark properly.
Exactly. And the suggested parameters, Section 4 talks about this, help keep evaluations consistent. Recommended action sets, number of times to repeat a task, maximum number of steps, things like that.
It's like a set of best practices for running experiments on a particular benchmark, making sure the results are reliable and comparable.
Precisely. This attention to detail is critical for moving web agent research forward. Now, one of the key strengths of BrowserGym is its ability to unify all these different benchmarks. How does it manage that, given how different these benchmarks are in terms of tasks and complexities?
That's a great question. It achieves this unification by providing a common interface for accessing and interacting with each benchmark. Section 3 explains this. It essentially abstracts away the complexities of each benchmark's individual implementation.
So whether a benchmark uses synthetic pages, like MiniWall-E, or real websites, like Assistant Bench, the agent interacts with them through the same BrowserGym API. Exactly. Researchers can switch between benchmarks easily, evaluate agents on the same tasks, and even create new evaluations by combining tasks from multiple benchmarks.
This cross-benchmark evaluation is important, isn't it? It really helps determine if an agent is truly capable of generalizing its skills, or if it's just overfitting to the quirks of a specific benchmark.
Absolutely. It's all about getting a more complete and robust assessment of what web agents can actually do.
Now, I remember you mentioning that some benchmarks need back-end preparation. What exactly does that involve?
Some benchmarks, Web Arena and Visual Web Arena, for example, rely on self-hosted web servers running in Docker containers. It's described in Section 4. These containers are like miniature versions of the websites the agents interact with.
So a controlled environment, isolated from the real internet to ensure consistency and reproducibility.
You got it. Section 4 also explains how these containers need to be reset to their initial state for each new evaluation.
Otherwise, the actions taken by one agent could affect the results for the next one, making the findings unreliable.
Precisely. And BrowserGym handles this backend preparation automatically. It uses a function called prepare backend. It checks the server, resets the containers, and makes sure everything is ready for a clean evaluation.
Like an automated lab assistant, handling all the tedious setup work so researchers can focus on the experiments.
Exactly. It's all part of the design of BrowserGym, user-friendly and accessible to anyone who wants to use it.
Okay, we've talked a lot about BrowserGym, the playing field, so to speak. Now let's shift our focus to AgentLab, the toolbox that complements it.
AgentLab, depicted in Figure 1 and described in detail in Section 5, is a key part of the BrowserGym ecosystem. It provides researchers with a powerful set of tools for creating, testing, and analyzing web agents.
So BrowserGym provides the arena, and AgentLab gives researchers the tools they need to design, train, and study their athletes.
Precisely. And like any good toolbox, AgentLab has a variety of tools for different tasks.
Can you walk us through some of the key features? What makes AgentLab so useful for web agent researchers?
Certainly. First, we have the study object, introduced in Section 5.1. Think of it as a central hub for organizing and managing experiments.
So like a researcher's lab notebook, where they keep track of all the details of their experiments, agent configurations, results, the whole 9 yards.
Exactly. Section 5.1 describes how the study object stores information about the agents, the benchmark, the parameters, and of course the results. It simplifies the whole process of running experiments, collecting data, and analyzing results in a structured way.
And I understand that AgentLab also supports parallel experiments,
Yeah.
which Section 5.2 talks about. Why is that important?
Parallel experiments are all about efficiency. Web agent evaluations can take a lot of computing power.
So instead of running experiments one after another, we can run multiple experiments at the same time, using the power of multiple computers or processors.
Exactly. Section 5.2 details how AgentLab does this using Ray or JobLib as backends. This lets researchers use their computational resources to the max, speeding up the research process.
Like having a team of researchers working simultaneously, each one focusing on a different aspect of the problem.
Great analogy. Now let's move on to one of the most exciting features of AgentLab, the Agent X-ray tool. This visualization tool, shown in Figure 9 and described in Section 5.3, allows researchers to watch, step by step, how an agent makes decisions during a task.
So it's like looking into the agent's mind, seeing how it perceives the web page, what information it focuses on, and how it arrives at its decisions.
Precisely. Section 5.3 explains that Agent X-ray displays the agent's observations, its actions, and even the internal prompts it generates. It's a very comprehensive and transparent view of the agent's behavior.
I can see how this would be incredibly useful for debugging errors, figuring out why an agent might be failing at a task, and even gaining a deeper understanding of how the agent reasons.
It's a game changer for understanding and improving web agents.
Okay, we've covered the study object for managing experiments, parallelization for speed, and Agent X-ray for visualization and analysis. What about creating new agents? Does AgentLab provide support for that?
Absolutely. AgentLab makes it easy to implement new web agents, as detailed in Section 5.5.
So if a researcher has a new idea for a web agent, they can use AgentLab's API as a foundation to build and test their creation.
Exactly. The core of the API is the agent class, as explained in Section 5.5. Researchers define a few key methods, the most important being getAction.
That getAction method is where the magic happens, right? It's where the agent decides what to do based on its observations of the web page.
You got it. And AgentLab provides a flexible framework for implementing that decision-making logic.
Now, AgentLab also has features that help with the challenges of working with large language models, or LLMs. Can you tell us more about that?
One of the biggest challenges, as described in Section 5.5, is handling the sheer amount of text on a web page. The content can be huge, way more than many LLMs can handle.
So just feeding the entire HTML or AX tree to the LLM might not work. It's like trying to fit an entire library into a small backpack.
Exactly. That's where AgentLab's dynamic prompting tools come in, which are explained in Section 5.5 and exemplified in Figure 11.
Dynamic prompting tools, how do those help? Do they act as filters, reducing the amount of information sent to the LLM?
You could say that. Section 5.5 describes how dynamic prompting lets researchers carefully control what information goes into the prompt set to the LLM. This ensures that the input stays within the LLM's limits while still providing the agent with the most relevant information for the task.
So it's like summarizing the web page content for the LLM, focusing on the elements and attributes that are most likely to be important for decision-making.
Exactly. And as explained in Section 5.5, these tools offer different ways to shrink the prompt, reducing the history of past interactions, truncating parts of the HTML or AX tree, even using techniques like set of marks to highlight specific elements for the LLM.
So it's like giving the LLM a tailored view of the web page, removing the clutter and guiding its attention to what matters most.
Precisely. AgentLab makes it easy to implement these dynamic prompting strategies, which is a huge help for researchers working with these large language models.
Now, we discussed the importance of reproducibility earlier. Does AgentLab offer specific features to ensure that experiments can be replicated accurately?
Absolutely. AgentLab has several features designed to improve reproducibility. It's all detailed in Section 5.4.
Can you give us some examples of how it does that?
One important feature, mentioned in Section 5.4.2, is that it keeps track of all the software versions. Even small changes in the code of a library or dependency can sometimes significantly alter results.
It's like writing down the exact ingredients and measurements in a recipe. If someone wants to make the same dish, they need to know exactly what went into it.
Perfect analogy. AgentLab meticulously records all the software versions used, which makes it easier for others to recreate the experiment precisely.
Makes perfect sense. What other measures does AgentLab take to ensure reproducibility?
It also enforces the use of those standardized observation and action spaces that we talked about earlier. Section 5.4.2 covers that. This makes things consistent across different experiments and reduces discrepancies caused by variations in how information is presented or actions are performed.
Like a universal rulebook for the game, making sure everyone is playing by the same standards.
Exactly. Then there's the reproducibility journal. It's built into the study object, as described in section 5.4.2. It logs all the essential experiment information from timestamps to benchmark versions, package versions, commit hashes, even the operating system details.
So a comprehensive logbook capturing every detail makes it easier to track down any potential sources of variation when replicating the experiment.
Precisely. And AgentLab goes a step further with the reproducibility agent. We touched upon this earlier. Section 5.42 describes it. This agent reruns actions on a task to check for consistency. It even highlights any differences visually between the original run and the replication.
So it's like having an independent auditor double-check the experiment for any signs of inconsistencies.
Exactly. This is what makes AgentLab so valuable for reliable and reproducible web agent research.
We've seen how AgentLab streamlines creating, testing, and analyzing web agents.
Right.
But how does it handle integrating different large language models? There's a lot of them out there, all with different APIs and capabilities.
That's where AgentLab's base class for LLMs comes in, as explained in Section 5.6. It allows researchers to plug in their preferred LLM no matter the API or functionality.
So it's like a universal adapter able to connect to different types of plugs, ensuring compatibility across LLM providers.
Perfect analogy. AgentLab also comes with predefined classes for popular models like OpenAI, Azure OpenAI, and OpenRouter. Section 5.6 lists these. It makes it so much easier to start using these LLMs without writing a bunch of custom code.
So like having pre-built connectors for the most common devices, making setup much smoother.
Exactly. These classes handle the API stuff and even provide helpful tools like cost and token trackers.
So researchers can keep an eye on how much those API calls are costing and how many tokens they're using. Essential when working with large, powerful, and sometimes expensive LLMs.
Exactly. AgentLab takes care of the practicalities, letting researchers focus on the more exciting stuff.
You mentioned earlier how AgentLab uses dynamic prompting to work around LLM limitations, especially with large amounts of text. Can you give a real-world example?
Sure. Imagine using an LLM to control an agent on a complex website, like Amazon. Section 5.5 uses this as an example.
Okay, picturing a massive website with tons of products, categories, filters, reviews, images, text the works.
That's it. Now, Section 5.5 explains this. If you just feed all the HTML from that page to the LLM, it would be way too much.
Right. The HTML for a website like Amazon would be gigantic.
Exactly. So instead of bombarding the LLM with everything, dynamic prompting lets researchers pick and choose what information is included. Section 5.5 talks about this in depth.
Okay, so how would that work with Amazon? Let's say we want the agent to find a specific product, a wireless noise-canceling headphone, for example.
Instead of giving the LLM the entire HTML, you would focus on the product listings. Just the titles, prices, maybe some key features.
Filtering out all the unnecessary stuff.
You got it. And you might include information about filters the agent has already applied. If it's already looking at headphones, you don't need to give it information about other product categories.
So the prompt is tailored to the specific task, making sure the LLM gets the most relevant information without getting overwhelmed.
Precisely. This prevents overload and helps the LLM focus on the most important aspects of the web page that can lead to better decision-making.
It's like giving the LLM a zoomed-in view of the web page, cutting out distractions and highlighting what matters.
Exactly. And AgentLab, as described in Section 5.5, gives researchers the tools to implement these dynamic prompting strategies easily. It's a big help when working with LLMs in complex web environments.
Now let's talk about the generic agent mentioned in Section 6. It sounds like a valuable tool for evaluating different LLMs on a level playing field.
It is. Section 6 describes the generic agent as this baseline implementation. It lets you compare different LLMs across different web agent tasks, like having a standard athlete with interchangeable brains, those LLMs to see how they perform in the same challenges.
So you can isolate the impact of the LLM on the overall performance by keeping everything else the same.
Exactly. And Section 6.1 explains how the generic agent uses a modular prompting mechanism. This allows researchers to experiment with different prompting techniques.
Modular prompting techniques. Can you give us some examples?
Sure. As detailed in Section 6.1 and shown in Figure 11, the generic agent allows you to use things like chain of thought reasoning, where you prompt the LLM to think step by step. It supports using screenshots or set of marks for visual grounding, helping the LLM connect textual instructions to visual elements on the page. And it even has a memory mechanism, so the agent can remember past interactions and use that information for its current decisions.
So you're giving the agent different cognitive tools and strategies. You can then see which approaches work best for different LLMs or different types of web tasks.
Exactly. That modularity is one of the best things about the generic agent. It's a very versatile tool for exploring LLM capabilities in web environments.
The paper also mentions the generic agent has a retry functionality. What's that for?
Working with LLMs in web environments can be unpredictable. Section 6.1 touches on that. Sometimes the LLM generates an output that doesn't translate into an action, or it might not respond at all because of network issues or rate limits.
So the retry functionality is there to handle those occasional hiccups without stopping the experiment altogether.
Exactly. As explained in Section 6.1, the generic agent can retry several times before giving up on a task. It helps ensure that failures are genuine and not just temporary glitches.
That's smart, makes the experiments more robust. The results reflect the agent's true abilities. Okay, now I really want to hear about those experiments. The researchers put this ecosystem to the test. What were the key findings? What did we learn about web agents?
Well, Section 6 describes a large-scale evaluation. They took 6 state-of-the-art LLMs and tested them across all the benchmarks we discussed.
So they really put those LLMs through their paces on all those different playing fields, testing their abilities on a variety of web tasks. And what did they discover?
The main goal was to understand what these models are capable of and identify areas where they need to improve. The results are in Table 2, and they're really interesting. One thing that really stands out is the performance of Claude 3.5 Sonnet.
So Claude 3.5 Sonnet was the star athlete, consistently outperforming the others and showing a high level of proficiency in web tasks.
Exactly. It achieved the highest success rates on almost all the benchmarks, including the complex tasks of MiniWo, WorkArena, and even WebLonix.
Impressive. But what about the other models? How did they perform compared to Claude 3.5 Sonnet?
GPT-4o and GPT-4o Mini, those are the powerful models from OpenAI, performed decently. However, they were consistently behind Claude on most benchmarks. Interestingly, GPT-4o showed a significant improvement compared to its previous performance on WebArena and WorkArena L2.
So GPT-4o might not be at the top yet, but it's steadily getting better.
Exactly. Suggests that OpenAI is making progress on improving their model's capabilities for web reasoning.
What about those open source models like Llama? I imagine they might not have as much development power behind them as the OpenAI and Anthropic models.
Yeah.
How did they fare in these evaluations?
They actually did surprisingly well. The Llama models, particularly the 405B version, even outperformed GPT-4o Mini on several benchmarks.
That's impressive. It shows that innovation in AI isn't limited to big companies with tons of resources.
Exactly. This finding is quite encouraging. It suggests that open source models can be competitive, potentially leading to a more diverse and accessible AI landscape.
We've talked about the overall performance across different benchmarks. Were there any benchmarks where the models struggled or did unexpectedly well? Any surprises in the findings?
There was one surprising observation. All the models, even Claude 3.5 Sonnet, had relatively low scores on Assistant Bench. This was unexpected because Assistant Bench is specifically designed to test information gathering skills, which are crucial for real-world web agents.
So even the top performers stumbled on this one. That's interesting. Why was Assistant Bench so challenging?
Section 6.2 explores this. They speculate that the BrowserGym API might be more geared towards direct browser manipulation, things like clicking buttons and filling forms, rather than complex information gathering and synthesis, which Assistant Bench is all about.
So it's like they have the tools to interact, but not necessarily the skills to truly understand and extract meaning from the information on the page.
That's right. This finding highlights an area for future improvement. Perhaps the API needs to be enhanced to handle tasks that require deeper information processing and reasoning.
So while we've made great strides in web agent technology, there's still room for growth, especially when it comes to those complex, information-rich tasks that are becoming increasingly common online.
Absolutely. The BrowserGym ecosystem is a great platform for exploring these challenges. It's a testament to the collaboration in the research community to build a robust and versatile framework for evaluating and improving these AI systems.
So we've talked about the exciting stuff, what BrowserGym can do, those promising results. But what about the limitations? Where are the challenges and what's next for web agents?
Great questions. Section 7 dives into that limitations and future directions. One thing, even with all that focus on reproducibility, is just how much real-world websites change.
Yeah, that makes sense. Websites are constantly being updated, redesigned. Even the content can change from one minute to the next. Must be tough to keep those evaluations consistent over time.
It is. Section 7.1 highlights that even small things, like language differences based on location, can cause problems. Imagine an agent trained on a website in English. What if that site defaults to a different language based on where the user is?
That could definitely throw the agent off. It's just how complicated those human web interactions are.
Exactly. And then there's the issue of robot detection. Section 7.1 talks about this too. Lots of websites use things like CAPI-TCHAs and rate limiting to stop automated access. That's a big hurdle for web agents.
It's like a constant battle. Websites trying to keep bots out and researchers trying to get their agents in.
It is, especially for benchmarks like Assistant Bench, which use those live websites.
That brings up safety and security concerns. If these agents are interacting with real websites on our behalf, we need to make sure they can't be hijacked or misused.
Absolutely. Section 7.1 specifically talks about that risk malicious actors controlling an agent and using it for bad stuff, accessing sensitive data, doing things they shouldn't. Security is super important here.
It is, especially as this technology gets more powerful and integrated into our lives.
For sure. Another limitation, Section 7.1 brings this up, is what they call agent collisions. Imagine multiple agents all trying to do stuff on the same website at the same time, adding items to a cart, booking appointments, that kind of thing. Their actions could interfere with each other, causing unexpected results.
Like a digital traffic jam, everyone vying for the same resources and potentially messing things up for each other.
Exactly. This is especially a problem for benchmarks like Web Arena and Visual Web Arena, where those agents are essentially in the same virtual space.
Right. It makes it harder to isolate the actions of one agent from another, which could skew the results.
Exactly. And then there are limitations because of how the BrowserGym API works. Section 7.1 mentions this. Everything's done sequentially, one action after another, can cause problems for tasks that need quick back-and-forth interaction.
Like trying to have a smooth conversation, but having to wait forever for a response after each sentence totally disrupts the flow.
Perfect analogy. Shows we need more research into how to make these interactions more fluid and efficient. So we've talked about reproducibility, safety, agent collisions, limitations of how the API works. What about the future? Where is this all going?
Yeah, what are the researchers excited about?
Section 7.2 lays out some promising research avenues. We need to improve safety mechanisms, like we talked about, to make sure these agents are used responsibly and ethically.
Safeguards to prevent unauthorized access, protect sensitive data, ensure ethical behavior.
Exactly. Another big one is developing real-time web agents. Section 7.2 focuses on this. Right now, most agents work in this turn-based way, but real-world interactions need fast responses. Think real-time chat, browsing at human speeds, participating in auctions online.
That would be cool to see.
It would. It'll take advancements in how quickly the agents process information and make decisions.
So making them quicker on their feet.
Exactly. And we also need smaller, more efficient LLMs. Those large models like GPT-4 are great, but they need a lot of power, not ideal for things like phones or smart home devices.
Right. Not everyone has access to a supercomputer.
Exactly. Section 7.2 emphasizes finding that sweet spot. Smaller models that can still handle complex web tasks make the tech more accessible.
Like a powerful but fuel-efficient car engine.
Great analogy. The paper, Section 7.2, also points to using computer vision language models, or VLMs, combine visual and textual understanding. Imagine agents that can compare images, grasp layouts, understand charts and graphs.
Now we're talking. Agents that can truly see the web, just like humans.
Exactly. Opens up a lot of possibilities. And of course, making those LLMs even faster and more efficient for web tasks is key. Section 7.2 talks about this too.
Like fine-tuning their cognitive abilities.
Right. This could involve shrinking the models without losing performance, training smaller models to copy the bigger ones, even developing specialized hardware.
Streamlining their thought processes.
Exactly. And as Section 7.2 mentions, all the data collected from the BrowserGym ecosystem can be used to train and improve these agents even further.
A constant cycle of learning and improvement.
Exactly. This data-driven approach is key for pushing the boundaries. We've talked a lot about the technical stuff, but I'm curious about the bigger picture. How will all this impact society?
The paper does mention some potential benefits and concerns, right? It does. Section 8 talks about the broader impacts. One of the big potential benefits is automation, freeing up human time and resources. Section 8 goes into this.
Imagine having an army of digital assistants handling all those tedious, repetitive tasks we do every day. Exactly. Could lead to higher productivity, lower costs, and more time for creative and strategic work.
Sounds great, but the paper also mentions job displacement, right? What happens to the people whose jobs these agents might take over?
That's a real concern. And Section 8 emphasizes the need to address it head-on. We need to think about retraining programs, social safety nets, and new economic models that account for a changing work landscape.
Making sure that everyone benefits from technological progress, finding ways for humans and AI to work together.
Absolutely. And beyond the economics, Section 8 also talks about AI safety and ethics. As these agents get more powerful and independent, we need to make sure they're not used for harmful purposes.
Right, they need to operate ethically in line with human values and social norms.
Exactly. That involves robust security measures, ethical guidelines for developing AI, and ongoing research to identify and mitigate potential risks.
It's a big responsibility for everyone involved, not just the researchers.
It is. So, as we wrap up this deep dive into web agent research, what's the key takeaway? Web agents are a powerful example of human ingenuity. The advancements in AI are truly remarkable, but we have to be aware of the challenges, the ethical implications, and the impact on society. Open collaboration, safety, ethics, thoughtful discussions about responsible AI. These are all critical for shaping a positive future for everyone.
Couldn't have said it better myself. Well, there you have it, folks. That concludes our deep dive into web agent research. Thanks for joining us on this journey of exploration and discovery. Until next time, stay curious, stay informed, and stay engaged in shaping the future we want to create.